All right, morning, everyone. I hope you're all enduring this ridiculous October weather. This is this is the worst I've ever seen here. So, I mean, this, I'll take a week or two of single digits here and there, but not in October. Like, cut us some slack, Anyhow, hopefully this means a mild February or something like that, which we've actually had the past couple of years. So, okay. I want to continue today with like the big vertex coloring theorem. Okay, so let's just recall real quick. Last time we proved that the chromatic number of G is at most the maximum degree of G plus 1. That was the greedy bound. That was very easy. That was just start coloring, never use a color that you shouldn't, right? That's on, never put a color that's the same as one along an edge, on the other end of an edge. And basically the only problem you run into is when you hit vertices of maximum degree. It's possible that all their neighbors have been previously colored, and in the worst case, they might all get different colors. And in that case, as long as you had one more color available, you always be safe to color that one. Okay. And just remember, what's the chromatic number, right? We're trying to color the vertices of a graph. So assign, say, numbers to the vertices of a graph, so that no vertex is adjacent to like whatever color it gets, it doesn't see on any of its neighbors. Okay, so, or no edge is monochromatic, right? No edge has red and red on both ends. Okay, and the chromatic number is the smallest value for which you can do that. Okay, all right. And so the big theorem here is Brooks's theorem, which for a fair amount of work says the following. Well, okay, we have to add actually a little bit here. So let G be connected. You don't need connectivity for this to hold, but to actually go through the proof, you might as well assume it's connected. So usually Brooks is stated with G is connected. If it's not, the statement's a little bit uglier. So let G be connected, and as long as, so if G is not one of the following two graphs, a complete graph or an odd cycle, then we can get a savings of 1 from the greedy bound. Okay. So let's just look at something. Why are the complete graph and odd cycle sort of identified out here? So the odd cycle, so any odd cycle, right? Just to take a 5 cycle, for instance, here, has max degree 2, but requires 3 colors. So this thing couldn't hold, right? Its chromatic number is higher than its max degree. Of course, the greedy bound still holds, okay? So this one, there's no way to improve it. And the complete graph has a similar issue as well. Say you take a K4 here. The max degree is 3, but you need a different color for each vertex, right? The max degree is 1 less than the number of vertices. So this also has no chance of holding, although again, the greedy bound does hold, okay? The reason we throw connectivity in here is if you say it's not connected, then you have to say that there's no component that's equal to one of these with the appropriate degree, blah, blah, blah. It's just an annoying mess. So just work with a complete connected graph and throw out these 2 examples, right? It can't be any complete graph, not just the K4, and any odd cycle. Every other graph, you can get an improvement of 1 to the upper bound here in the greedy bound. And let me highlight something here, that despite the fact that this is the best sort of general upper bound you can get, because there are other examples where it's also sharp, this gap between delta, chi and delta can be arbitrarily large. Okay, so there are graphs where the gap's big, like look at, for example, just a complete bipartite graph, right? So complete bipartite graph has all edges between here. It has chi equals 2, but its max degree is just, the size of one of the classes there. So the max degree says something like n over 2. So you can make those as far apart as you want, but you can also come up with examples where delta chi of G is equal to delta of G in general for infinitely many graphs. So you're not going to be able to improve this in general, but it does beat this one here. And so in some sense, it's the best we can hope for. Okay. I want to give 2 proofs of this theorem today. There's 2 different strategies. Let me say out loud what they are first. So 2 strategies for coloring anything is either get some coloring maybe by induction or by minimal counterexample, and then try to extend that coloring to G. So color some subpart of G and then try to extend it somehow. and by recoloring. So changing colors safely and then be like, oh, now I can color the vertex that I removed safely. That's one strategy. The other strategy, which is really similar but in disguise, is find an appropriate ordering of the vertices so that the greedy algorithm gives us delta instead of delta plus 1. So if we're smart, right, the greedy algorithm only gives us delta plus 1 if we're incredibly unlucky, right? We reach a vertex, all of whose neighbors are colored with different colors. Like if we can avoid that, then we'll only need delta colors, okay? So those are the two strategies. Okay, so before I prove that, I'm gonna state a proposition or a lemma that we're gonna use in both proofs essentially. And it's like it's a subcase of Brooks's theorem will be an exercise and is relatively easy to prove, okay? So the proposition says that if G, well, let's say is connected and has a vertex X with degree D of X strictly less than the maximum degree, or actually, I don't think we're going to use this in today's proofs, but or G has a cut vertex, then chi of G is at most delta of G. Okay, so this is like a baby Brooks's theorem. Let me just say the proof is exercise. But the idea is find a good ordering and greedy. Okay, and there's two cases. One, if you have a vertex of degree less than the max degree, and the other is if you have a cut vertex. Okay, this proposition is not very hard to prove. And actually, notice I didn't mention complete graph or odd cycle, but that's fine because in the complete graph and the odd cycle, this vertex doesn't exist, right? There's no vertex of degree lower than the max degree in an odd cycle or a complete graph. So the proposition doesn't address those cases, which it shouldn't, right? Because they're separate, okay? And if you think about it for a second, this actually captures like 99% of the graphs because this scenario here says there exists a vertex of degree less than the max degree, says that in Brooks's theorem, all we have to focus on is when all the vertices have the degree max degree, right? So it's a regular graph is what Brooks's theorem has to address, because as soon as you have a vertex smaller than some other vertex, this proposition takes care of it, okay? But this is not hard to prove. Like this proposition is not that difficult. I want to leave it as an exercise, but we will use it as a tool. So somehow what's hard in Brooks's theorem is if you have a graph that's regular and at least two connected. Okay, that's what takes the bulk of the work, okay? All right, but we'll apply this proposition here along the way. Okay, so let's start with a proof of Brooks's theorem. Proof of Brooks's theorem. Okay, so first we're going to need, and this is going to work in both proofs. So let's remember this for the second proof. So this is proof 1 of Brooks's theorem. Let's rule out the case when delta is small. I want delta, which is the regularity of the graph. Okay, so why don't we even say? Well, I'm thinking here. What's the best way to do this? Yeah. Okay. So by proposition, we can assume G is delta regular. Right? Because as long as you have a vertex of lower degree, proposition says it's done. I'm not going to write it down now, but we can also assume there's no cut vertex. Well, maybe I'll say it. And no cut vertex. There's many different proofs of Brooks's theorem. Some use different things here. I think we're going to be able to avoid using the cut vertex property. That's not going to be relevant to us. Okay. But we can assume it's delta regular. Every vertex has degree delta. Okay. So just to rule out a couple things, when delta equals 1, what does a connected graph with max degree 1 look like? There's only one option. It's just the single edge, like that guy there. And we don't have to address that one. That's a complete graph, right? Brooks's theorem doesn't weigh in on a complete graph. So we don't, that's out. What about when delta equals 2? What's a connected graph look like that's 2 regular? What's that look like? It's a cycle, right? Yeah, G is a cycle. And either it's an odd cycle and it doesn't have to be addressed. So if it's odd, we don't have to address it. And if it's even, well, in an even cycle, does Brooks's theorem hold? The max degree is 2. Is there a 2 coloring of an even cycle? Yeah, just alternate 1, 2, 1, 2, 1, 2, 1, 2 works. So great, that works as well. Okay, so the delta equals 2 case was simple. Delta equals 1 actually didn't even come into it. And so now we can assume that delta is at least 3. Okay, so every vertex has degree delta, and delta is at least 3. Okay, so now let V be an arbitrary vertex of G, and consider the graph G minus a vertex V. So pull that vertex off. This graph is delta colorable by the proposition, right? If I remove a vertex from this graph G, so delta being at least 3 guarantees it has, at least 4 vertices for 1. But if I remove this vertex from it, the resulting graph has a vertex of degree less than delta. And it also has some vertices of degree delta. So it falls under the propositions scenario. It has a one vertex of degree smaller than another vertex. Okay, so we're going to use the fact that this has a delta coloring and somehow figure out how to color G. Okay, so what this says, let me draw a picture. And this will be like claim 1. Okay, so in both of the proofs today, I'm going to be proving them by appealing to pictures a great deal. Okay, it's just the notes will have it written out. Although this first proof is not written in the notes at the moment. I will get it up for you guys soon. But the pictures are just crucial for me. They're totally easy with the pictures, and the writing them down is kind of a headache. Okay, so claim 1 says that basically the picture looks like this. Here's V that I've removed, so I'm going to be drawing G every time here, and we're always going to be focusing on V. So I removed V from the graph, and so V had some neighbors in G originally, right? So these are the neighbors. This is V1, V2, V3, ... And then this last one we can call V sub delta, right? Just regular V has delta neighbors in the original graph G. Okay, and then if I remove V from the graph, I know that there is a way to color the remaining graph. The proposition says, oh, I have a low degree vertex, great, I can color it. So I can assume that these vertices V1 up to V delta have been colored by the fact that this can be colored. And I can moreover assume that they're colored in such a way that I can't immediately color V. Okay, so that means that actually these are going to get colors. I'm going to use blue for colors. Color 1, color 2, color 3, this is color 4, all the way up to color delta. If there's any repeated color around there, then there's an available color for V. Everybody see that? Like that, that's always safe. If a vertex sees 2 vertices of the same color, then among its palette, which are delta colors, one of them has not been used yet, right? According to it. So V would be safe. But this is the one case where I can't extend the coloring of G minus V to this one here, like when it sees all the different colors, and I can relabel colors so that V1 gets 1, V2 gets 2, V3 gets 3, right? We'll just use that naming convention there. Okay. So in this situation, so claim 1 is, no safe color for V yet. We're going to figure out, we're going to recolor things so that we do identify a safe color for it, but we can assume the coloring, so coloring of G minus V leaves no safe color for V, so that the picture looks exactly like this. Okay, and actually we can even say more, any coloring of G minus V, any proper coloring, maybe even, let me emphasize this, right? So G minus V is delta colorable. There might be different ways to do it, but no matter how you do it, every single time you come up, V is going to see all the different colors next to it. If it doesn't, then we can finish Brooks's theorem by saying, oh, just color V with the available color. Okay, that's going to be our strategy throughout. So that's claim 1. Okay, so now we're going to have to define a bunch of subgraphs. So let H sub ij be induced subgraph on vertices of color I and J. So all I'm going to do is just look at all the vertices of color I and j and all the edges that were between them in the graph G. That's what hij is. Okay, so in other words, hij is all, I don't know, edges that see colors I and j on end vertices. Okay. So it's a subgraph. Actually, I guess it's a subgraph of G minus V because V hasn't received a color yet. But yeah, so H12 is all the vertices just of colors 1 and 2 and all the edges that were among those. Okay, and you can do that for any pair of colors. Okay, so claim 2. Okay, yeah, interesting. Is that VI and VJ are in a component of hij together. Okay, so let's look at that. So if not, here's the picture. So we're just focusing on VI and VJ. Here's V, here's VI, here's VJ. Let's say they're in different components of this sort of two-colored graph here. Okay, so say VI is in this component here, or VJ is in this component here, and VI is in this component here, and they're not the same component, so there's no way to get across here. All the vertices inside of this blob here are colors what and what. So here we're looking at, these are components of hij. Everything in here is color I or J, right? That's what the subgraph I'm looking at. Anybody see a strategy for recoloring, say this part here? Yeah, good, Ethan. Let's swap colors I and J inside of that blob there. Because it's not joined to this blob here, it has no impact on this blob. I only swap the colors inside of here. 1 and 2, I and J replaced each other. So this vertex over here is color I, and this one started out as color J, but when I recolor, it becomes color I. That does not affect the overall coloring of G minus V, right? I mean, I recolored things, but it's still a proper coloring, right? Because anything else that was adjacent to these things, you didn't use colors I or J. So when I swap them, it doesn't create any conflict. And now this means there's a safe color for V, because V now sees, right? Its other neighbors were colors 1, 2, 3, 4, 5, 6, all the way up to delta. And now I've got an I and another I incident to V. So this means that J could now be, V could be colored with color J. It didn't see color J, and we'd be done, okay? So this contradicts claim 1, which said that under any coloring, it should see all the different colors, okay? So what it means is VI and VJ better be in a component together. If they're in a component together, what happens when I do the swapping trick? Then the colors on VI and VJ are interchanged. And so V still sees color I and color J just on different vertices, right? So we can expect that to happen. Otherwise, we can fix things, okay? So swap colors I and J to get a coloring with no J adjacent to V, okay? And that actually contradicts case 1, okay? So we can assume that hij has components, or a component that contains VI and VJ. Otherwise, we can do this swapping, all right? This is a strategy we'll return to later in the class as well. This is very handy. Okay, so now we can let Cij be the component of hij with Vi and Vj. Okay, so now we know this green component actually contains both of those. That's what claim 2 tells us. Okay, so what's claim 3? Claim 3 is that that component containing Vi, Vj is just a path and only a path. There's nothing else on it. It's just a path starting from Vi, ending in Vj, and nothing else comes off of it, okay? So claim 3, Cij is a Vi, Vj path. All right, and let's draw the picture again. So here's V, here's Vi, here's Vj. And then I'm looking at the component Cij, so I'll do it like this. So I know there's a component containing both of those things here, and I claim that it's just a path. Now there's definitely a VI, VJ path inside of the component because it's connected, right? But let's suppose it's not a path, okay? So if not, well, let me explain what happens. If not, look at the path from VI to VJ, say the shortest path. There is a shortest path from VI to VJ in this component. And if the component's not a path, then there's other edges incident to this path, right? There's other vertices in the thing, and like there's stuff like this, right? There has to be something like this. Namely, there's a vertex, at least one vertex on this path whose degree is greater than 2, right? According to inside this component. If not, there exists, sorry, y, the vertex y on the shortest. So I say the shortest because like pick a shortest, right? The one I'm discussing, you know, shortest VI. Okay, don't even say that. Let's just let this be P, right? P is a VI VJ shortest path. I just pick one, all right? So otherwise there exists a vertex Y on P with degree greater than 2, okay? Moreover, choose the Y with degree greater than 2 that's closest to VI, right? Like start walking from VI to VJ, and eventually you reach a vertex of degree 3 or greater, like let Y just be the first one, okay? Without logos of generality, Y is the first such vertex, okay? Okay, so now there's a little bit of case analysis here, but we're just gonna prove one of the two cases here, okay? So VI has color I to start, VJ has color J to start, and then Y is either color I or J, right? Just depending on where it falls in the path. If it was the next vertex after VI, it would necessarily be J. If it was 10 later or 8 later, it could be I or J. Like it obviously alternates IJ, IJ, IJ. Both cases are easy. Let's just suppose it's I, like VI, right? Say, it doesn't really matter. Just say it's that. But then what can you tell me about this vertex, and this vertex? The 3 that are adjacent to I are Y. Each of them are J, right? Because I'm looking in, I'm inside of Hij. So this is J, and this is J, okay? I should have chosen 1 or 2. Like I and J are kind of hard to distinguish a little bit. Like look for like this or like this, right? Okay, so what I want to do here is also recolor this path here. So notice Y is adjacent to 3 different J's, okay? Now think about my palette of colors. My palette of colors has delta colors in it. And this vertex I sees J, 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 and it itself is I. So there exists an L color that's safe for Y. I can recolor Y with L. Okay, and what's important is that L is not equal to I. So I can recolor it with a new color L because it sees 3 J's and it itself is Y. Ordinarily, if I haven't been colored yet, seeing 2 of the same colors means there's an available color for me, okay? But I need 3 repeated colors if I want to change from what I've been given, right? And you can check the numbers there, but that's what it requires. So I can recolor it with L, okay? And now, what can I do? Let me sort of zoom in on this picture. So I've got VI, and then I've got the path reaching Y, and now this is color L, right? And Y was the first vertex where this path like split off, okay? So everything here is of degree 2 all the way to Y. By the way, I should be careful with the parity here. So this is I, J, yeah, and then this is I, but it became L now, okay? What can I do here along this path?
The path is no longer in the component.
Ethan, you're super quiet for some reason. I don't know if others can't hear you, but I can't hear you at all. No.
No longer in the component.
I can't hear it, but I'm going to assume you're saying swap I and J along this path, right?
I think Ethan said the path isn't in the component anymore.
Okay, yeah, good, Max. And Ethan, if that's what you said, that actually works as well. So actually, you can contradict a previous argument by saying, hey, we've got a new coloring. And now okay, actually that works. Let's just appeal to that. Very good, Ethan. So in this, we've produced a new coloring and it's a valid coloring. And in this coloring, VI and VJ are no longer in a component with each other anymore. Sorry, they're no longer in a component of HIJ anymore. So keep the coloring as is. Yeah, that's even a better contradiction, okay? So keep the coloring as is, changing L here. That's a proper coloring. Now look at the new HIJ in this new coloring. In the new HIJ, VI is adjacent to everything over here and then blocked off by this new colored vertex. And J is incident to everything over here. So now in the new picture, there's a component that goes like this, a component that goes like this. This thing here might be part of this component over here. I don't know, I didn't change that vertex. There's other stuff. The point is though, VI and VJ are in separate components of HIJ, new HI, you could call it HIJ prime or something like that, which contradicts claim 2, the claim we were doing before. An alternative, what I was gonna say here is in this, what becomes a component, I can swap I and J colors here in the same fashion, right? If I swap colors I and J, this guy ends up with J, and then V sees J twice, and V has a free color. Both strategies work. It's the same thing, okay? So yeah, perfect. So this violates claim 2. Yeah, good. Ethan, that's good. Okay, one more claim. So now the situation we've got is pretty good. Let's claim 4, and let me start off just by drawing this one and explain what I'm talking about. So now we know that for every pair, VI and VJ, there's a IJ path between the two of them, right? And that's it in terms of colors I and J. There might be other colors incident to those guys, of course. And this is, we're gonna call this VL. So now I'm gonna look at 3 things here, and I know that there's a path CIJ, right? CIJ is the component of HIJ of colors I and J, and I know it's a path. That's what the previous claim says. And there's also a path from VI to VL. And what I want to rule out is the possibility of these 2 paths intersecting each other, okay? So what I'm going to say here is claim 4 is that CIJ intersect CIK is only equal to the vertex VI, right? VI is obviously in both those paths, but I want to rule out the following scenario that like the VL, what did I say? No, this is nonsense, right? Yeah. The intersection of 2 things, yeah, that's impossible. CIK is what I want here. So there's also a CIK path between, K, geez, all right. I don't know what I'm doing here. There's no K, CIL, IL. These 2 paths. I've got CIJ and I've got CIL. And what I want the picture to look like is that. That's what I want. I desire that. And I'll be able to finish the proof if I get there. And so let's suppose instead that the situation looks like this, that we go here and then we hit this thing and then eventually reach there. Okay. Obviously, there might be multiple intersections with the paths. They don't share any edges though, right? These 2 paths can't share edges because any edge on VL, VI has I on one side and L on the other side. And every edge on this path has I on one side and J on the other side. So they don't share anything, okay? But let's let this W be the intersection, okay? So if not, there exists a first intersection on, say, CIJ. It doesn't matter. So starting from I, there's a first instance where the 2 paths intersect, okay? First intersection, let's call it W. And let's zoom in on that as well. Okay, so look at W. And then, so W is on both the VI, VJ path, and it's also on the VL, VI path. Can you tell me what color W has to be? Here, there's no cases. Like, W has a color specified automatically. Yeah, it's got to be I, right? It's on the VI, VJ path, which is I and J colors, and it's on VL, VI, which is I and L colors. So it has to be I if it's in both of them simultaneously. That means that this vertex here is J, this vertex here is J, this vertex here is L, and this vertex here is L. And this means, similar to before, it's I, it sees L, L, and J, J. It means there's actually a color here that I can replace it with, say, K. I can recolor it with K safely, and K is not equal to I or J or L. I can recolor it with a new color, okay? Again, you got to check the numbers here in terms of delta, how many colors you have free, how many are available. I mean, you have to avoid, but it's fine. It sees these guys here. And then actually we can use now Ethan's contradiction again. Now W has been colored with color K. This broke the path from VI to VJ that was IJ colors. So now in this new coloring, HIJ has only this component here. And so I would violate claim 2 again, okay? So new coloring violates claim 2, that they were contained in the component. An alternative is I can recolor this blob here and get a repeated color for that guy there. Okay, so that's the last claim. Now we need to put all this together to prove the theorem, okay? So now let's look at the following picture here. Let's look at, so this is for the claim. Here's V, and now let's just use actual numbers. Here's V1 and here's V2. And finally, let's use the fact that the graph is not a complete graph, right? We've already used the fact that it was not an odd cycle, right, when we were considering delta, but we haven't ever used the fact that it's not complete. Okay, so now choose V. Remember V, the vertex we plucked off at first was arbitrary. It could be any vertex we want. So choose V such that it has neighbors V1 and V2, which are not adjacent. Okay. So I want to grab a vertex that has two neighbors that don't have an edge directly between them. Okay. This exists as G is not a complete graph. Okay. In a complete graph, you can't find such a vertex. In a complete graph, if I grab a vertex, all of its neighbors are adjacent to each other. But if for every vertex, all of its neighbors are adjacent, that's a complete graph. So the point is, I do have this scenario here where I can grab a vertex V and it has two of its neighbors, VI all the way up to V delta, that are not adjacent. So there's not an edge between these. However, there is a path, right? There's a C12. I just know that that path isn't a single edge, right? Before, in these previous arguments, maybe it wasn't perfectly clear, but you can allow for the situation that the path from VI to VJ was a single edge. The arguments still, they hold just fine there. Okay, some of them are vacuous because there's no vertex for them to intersect, but you know, like if it's a single edge, then all the properties are, you know, fine. There's no intersection along a single edge and so on and so forth, okay? Okay, so there is a C12, and the point is that there's a Y on C12 that's adjacent to VI that is not V2, right? So there's one intermediate vertex at least. There's a first one there, okay? All right, and then we also know that there's a vertex V3. The existence of V3 finally follows from the fact that delta is at least 3. We haven't used that yet either, right? We established that early on, but this vertex V that we pluck off was of degree delta, and delta was at least 3. So there is a V1, there is a V2, and there is a V3. And then there's also C13, right? There's a path from V1 to V3. That path, though, might be a single edge. That's a possibility, but it's definitely there. And by claim 4, it's definitely disjoint from C12. C12 and C13 don't share any vertices. Okay. Now let's look at colors, and we do a quick recoloring to finish the proof here. This is color 1. Y is necessarily color 2, right? It's on this path here. V2 is color 2, and then V3 is color 3. There may be no other intermediate vertices here or here, but we know we at least have these 1, 2, 3, 4 vertices here. Okay, and so now I want to do a swap here. Let me write them out here. So first I'm going to swap colors 1 and 3 on C13. Okay, so along this path here, I'm going to change 1 to 3, 1 to 3, 1 to 3, 1 to 3, 3 to 1, and then this guy here. Okay, just do the swapping along the path there. Okay, this hasn't saved me yet because vertex V here still sees color 1 and color 3 simultaneously. But now let's swap along this path here, 1s and 2s. Okay. Yeah, by the way, the fact that there's an intermediate vertex y here tells me that there's another intermediate vertex inside the path here, because y can't be adjacent to v2. Otherwise, you'd have 1, 2, 2. So it's not really important. But along this path now, what would have been the vi v2 path, swap 1 and 2. Okay. So what I'll say here is swap 1 and 2 on C1, 2 minus v1, right? v1 can't be swapped anymore because it's been changed to color 3. But now swap along this thing. So this becomes 1, this becomes 1, and then like an intermediate one here would become, it would become 2, and so on and so forth. Both these swappings were valid. They didn't produce a conflict because of the configuration of these paths. And now this coloring looks as like what? V now sees color 1 twice on V3 and on V2. So that means I can color V with color 2 safely and complete my coloring. I could only do this swapping because that these paths were disjoint, right? If they weren't disjoint, then the swapping on this might affect the swapping on this. And I also needed an intermediate vertex Y, because otherwise the swapping from V2 to V1, like I can't change 3 to 2 magically. Like you needed something along the way here to actually, so this path like terminated and there was a valid swap, okay? And that ends the proof. That's Brooks's theorem, okay? So this was the recoloring strategy, right? We got most of a free coloring from G minus V, and then we had to make some alterations to it to arrive at the thing that we wanted, to get a repetition color. Okay, all right. The second proof is much shorter, so we should be able to finish this one up in time. And this particular treatment of Brooks's theorem, although it adapts sort of the classic proof by Lovász, this treatment that I'm going to give now was presented only in like 2018. So this is like super new. The main idea is the same, but it cleans up some old arguments that, like if you look in which textbook? Actually, I think the D-Still textbook gives a proof basically like the one I just gave above here. So if you do want a reference for it, it's in there. This proof, I don't know which book, like the old version of this appears in. Anyway, all right, proof 2. This is the new one. Okay. So as before, we can assume that G is delta regular. And we can also assume that delta is at least 3. Right in the beginning of Brooks' theorem, we took care of the case that delta was 1 and delta was 2. Those two things were fine. Okay. Okay. And what's funny is this proof kind of starts where the last one ended. Okay. So where the last proof ended, we grabbed a vertex that had 2 neighbors that were not adjacent to each other. That followed by the fact that it was not complete. Okay. So as G is not complete, pick a vertex. We're going to name it V2. All right, now the naming convention has nothing to do with the previous, with non-adjacent neighbors V1 and V3. Okay. So I pick a vertex V2, which has a neighbor V1 and a neighbor V3. This configuration exists because it's not a complete graph, right? We just discussed this a moment ago. Okay, so now we're going to take a longest path. So let P be a longest path starting with V1, V2, V3. Okay, so you start V1, V2, V3, and then you just go as far as you can until you get to some VR. Okay, so that's the longest path starting with those 3 vertices in that order there. Okay, and so we'll name P equals V1, V2, V3 necessarily, then V4, all the way up to VR. So take a longest path that looks like that. Okay, and the usual fact that we'll use here is that VR's neighbors in the graph all go back onto the path, right? Otherwise, if one went out, we could extend the length of the path here. Okay, so yeah, so before we finish the proof here, let me explain our strategy. Our strategy here is to choose an ordering of the vertices so that when I go through and color the things greedily, I will always be safe at every moment. I'll always have an available color among my only delta colors, okay? The easiest way to have that strategy is if I'm at a vertex and it has one neighbor that hasn't been colored yet, then I'm definitely safe, right? Max degree is delta. If I've only colored delta minus one of my neighbors, then there's a delta color available for me. Now I can't do this forever. Eventually I reach the last vertex and it won't have an uncolored neighbor. So the whole thing, this whole strategy, and actually I gave away the proof of the proposition basically, sort of. The whole strategy is to make sure that when I reach the end, I'm not stuck. But if at every intermediate step I take care that, hey, there's an uncolored neighbor, then I'm safe, okay? Except for the end I have to resolve somehow. Okay, so case one is if this longest path happens to just be Hamiltonian and uses every vertex. What's going on here? Oh, okay. So case one, that's when R equals N. So every single vertex got used up by this path here. All right. So let's look at a picture here. So V1, V2, V3, and then all the other vertices until I reach Vn. Okay. So I know that there's some Vj that's adjacent to V2 that's not V1 and not V3, right? V2 has degree at least 3. Every vertex has degree at least 3. So V2 has a neighbor Vj like that, okay? Does it even matter which one? No, I don't think it matters. So let Vj not equal to V1 or V3 be a neighbor of V2. And this exists by the fact that delta is at least 3. Okay, and now let me just draw in the picture. We're gonna color the vertices in the following order. Start off by coloring V1 and V3. They both get the same color because by construction, V1 and V3 were not adjacent to each other. Okay, so they'll get color like, I don't know. I don't want to, let me do like a check mark for when they're colored, and then we'll confirm that they're okay. So V1 and V3 get colored first. Okay, so like when you look at these notes after the fact, you're not going to be able to tell what happened. So it's good that you're here. But so those are the first ones we're going to color. Then we're going to color, let me add a couple vertices here. We're going to color V4, V5, all the way up to Vj minus 1. Okay, so we're going to start from V4 and just start coloring going that direction. Okay, so then the next steps are color V4. V4 is safe because there's an edge on the path here that V5 hasn't been colored yet. So no matter what neighbors of V4 have already been colored, right? V4 might be adjacent to V3 and V1. It doesn't matter though, because it has one uncolored neighbor. So V4 is safe, V5 is safe. All up to Vj minus 1 is still safe because it's adjacent to Vj, which hasn't been colored. Okay. Now I'm going to go jump ahead to Vn. And Vn has a neighbor that's not been colored by looking in the reverse direction, right? You can just fill in everything there. Vn says, hey, wait, I have a neighbor who hasn't been colored. Maybe some of the neighbors of Vn have been colored, right? Maybe some of these have been colored, but this edge, that hasn't been colored. So Vn can be colored, then that can be colored, that can be colored, that can be colored, that can be colored. And then I continue all the way until I get to Vj. Why is Vj safe to color? It doesn't have anything on, everything on the path has been colored now, but Vj is adjacent to V2, which hasn't been colored yet, right? So Vj was also safe. And so now I've reached the very last vertex, V2. Every single one of its neighbors has been colored. So in principle, there's a conflict, except why am I safe here? Because of how I started. V1 and V3, they got the same color, right? Because they're not adjacent. So V2, even though everything's colored, still has a safe color because of the repeat. In all the other steps, I couldn't guarantee repeats, but I could guarantee an uncolored neighbor. Okay, so that's it. Very simple strategy there. That's if R equals N. The other case I need to address is when R is less than N. Okay, so when the path doesn't eat up everything. But super simple, especially as an algorithm. That's how this is described in the paper. Okay, so case 2 is that R is less than N. Okay, and so I'm going to do a similar strategy. So here's V1, V2, V3, and then all the way up to Vn. And then from Vn has neighbors and they're all on the path. Sorry, not Vn, Vr, right? There are other vertices too. Vr is, R is less than N. So now I want to look at this. Vj is defined differently now. Vj is neighbor of VR with lowest index. Do I even need the longest, the start with V1, V2, V3 for this? Huh. Yeah, I don't know. Interesting. We'll see here. Okay, so VR's neighbors all live on the path by the fact that it's the longest path. So maybe that's what I need. And VJ is the earliest one along that path. So all the other neighbors of VR like are inside of this part here. Okay, but the point is, actually that's part of the point, but the real point here is that from VJ to VR and back, that forms a big cycle, right? That's a cycle C. Okay, so I've got C here. And on it is VR. And there's also VJ. And those happen to be adjacent to each other. What? Wait, whoa. No, so, no. I mean, that's crazy. VR and VJ are next to each other on the cycle. What? I mean, I don't think that's a problem. I'm just, okay, so let's put VJ here. This is my cycle C that I got from up here. All of VR's other neighbors are inside of this cycle. And let's let this be the rest of the graph. Okay, so this is G minus, let's be clear, this is G minus the vertices of the cycle C there, okay? Okay, now as my graph is connected, there's got to be at least one edge between those two things there, okay? The existence of this edge means that this graph here, G prime, this is G prime, has a delta coloring by the proposition, right? If I remove this cycle here, what I'm left with here, not all of its degrees can be delta because at least one vertex in here sent an edge over to C. So it has at least one vertex of degree less than delta. So there's a delta coloring by the proposition, right, that we used early on. Call this, say that's U, and delta color that, okay? And I need to extend it to the cycle somehow, okay? And so how am I gonna do that? Let's let this vertex be VL such that L is largest index with VL adjacent to this G prime, okay? So VL is the highest index that's adjacent to something there. First observe that L is definitely less than R, right? VR does not send an edge to G prime. It only sends edges inside of the cycle C, right? That was literally the description here, right? VR to VJ was a cycle and all the edges are inside of that cycle, so they don't go out of the cycle. By the way, these vertices here, they're part of G prime, right? Some of these initial vertices are part of G prime and all these other vertices are part of G prime. I'm only looking at this part here, this cycle. Okay, so this means that VL plus 1, which might be equal to R, that doesn't send any edges across, right? Because VL was the biggest one, so the next one doesn't. Okay, and so now I'm going to color in the following way. Where do I start? Yeah, so let's go as follows. Everything here is colored with delta colors, and on U, say it sees color 1. Let's say, right? I don't know what it is. It's done by the proposition. I'm going to start coloring the cycle first by coloring VL plus 1. What color will necessarily go on VL plus 1 by the greedy algorithm? Well, I mean, okay, that's not fair. The point is I can color this with color 1, right? That's the first vertex to be colored, and I can use whatever color was on U for it. So that's what I'll do, okay? And now I'll just go around the cycle and color. So VL plus 2, plus 3, I can just keep coloring these until I get to VR could be colored. Because they're on a cycle, they always have a forward neighbor that hasn't been colored yet, just like the same thing as before. Then VJ can be colored and keep going around the cycle until VJ, and then keep going until I reach, oh yeah, okay, I'm fine. Just keep going around the cycle. This is even easier than I thought. Reach here and color that guy. Now, look at VL. Can I color VL? Yeah, it's adjacent to 1 and to 1. Done. Actually, so that's the end of the proof. Same strategy here. It seems to me, actually, this proof could be cleaned up even further because the existence of V1, V2, V3, and the fact that they were non-adjacent was irrelevant. all I needed was a cycle that had a vertex, at least one vertex that didn't send edges across there. And then actually, what I could have even VL. Yeah, I needed a VL that sent an edge and a VL plus one that didn't send an edge. That was the whole key, because then I ended up with repeated neighbors of VL. And that for that to exist, I needed a cycle that wasn't everything, but that was the first case. So anyway, it doesn't matter. I'm just thinking out loud here that maybe the proof can be cleaned up a little even further than this. But that ends it. And you can see this is maybe a little more desirable than the first proof. Different strategy, right? It's not a recoloring, it's a direct coloring with a clever ordering to the vertices. It sort of more clearly jumps out at you that it's correct. Okay. All right, good. So that'll do it. On Wednesday, we will talk about something very cool about colorings. So yeah, I'll just leave it at that. Good. I'll stick around for questions or whatever.
So for today's homework, can we assume that the graphs are connected, or do we have to work with disconnected graph also?
Oh, I see. You mean for the, like, yeah. Which I mean, I think connected's probably always okay. Which is there one problem in particular that you're thinking about when that comes up?
Let's see. Let me check my homework.
But I mean, almost all problems here for planarity and for coloring, it's, you know, you can just say that if you can prove it for a connected part, like a component, then you can prove it for everything individually, right? So like that, it's almost always safe to just assume that, but just make sure it's clear from the problem. Most of the things I've assigned, I hope that that you know, non-connected didn't yield a different case than connected, right?
Okay.
So yeah, so basically the answer is yes. So,
okay.
Yeah. Ethan, any question for me? Ethan, I don't know what it is, but your audio just doesn't come through for me. I don't know why. Maybe now? I can hear your keyboard.
Oh, my audio was set to the wrong setting. Okay.
Ah.
Because I have a headset and headphone. Oh, I can actually put video on. Since I'm at
Sure.
school.
Yeah. Gotcha.
Yeah. I have a headset and headphones, and I forgot to change it to headphone mode.
Yes.
So it was trying to use the, I don't know how these have a mic in them, but they do somehow.
Sure. Yeah, I have a set just like that
that
I use for my phone, and I have no idea where the mic is, but.
Yeah. All right. I was wondering, I noticed while completing this homework, I noticed the best or the easiest way for me to get a proof for my problem was to start with the proof in the notes and
Okay.
change it.
Yeah. Which problem?
I think I did it multiple times.
Okay. Yeah. No, I mean that's fine actually. That's desired.
Okay.
Like for number 6,
Yeah.
certainly you adapt the proof that we did in the notes. And yeah, absolutely.
Yeah. I just wanted to make sure that it was fine because.
Yeah. No. Actually,
I just thought of it in the middle of the night. I was like, wait, is that actually plagiarism? I don't know.
No. Yeah, it's a good question, but yeah, I actually wish I could ask more questions of this type. That here's the proof I presented with you, and actually, if you modify it, you can prove something stronger. This is a good instance. I think number 3, number 6, certainly, maybe number 4. A lot of them use similar ideas.
Yeah. All right. I just wanted to make sure that was fine.
Yeah. Sure.
Thank you.
Yeah, no problem.
See you Wednesday.
Yeah, you bet. Take care. See ya.